Welcome Math 107 students to the class activity for Lesson 2 on mathematical models, algebraic expressions, and real numbers. So in this class activity, we're asking you to take a look at the idea of the union and intersection of sets. So the first question here says, the members of the 1961 rock band, the Beatles, that performed in Hamburg, Germany, was not the same as the Fab Four that arrived in the US in 1964. So let set A, capital A, represent the members of the 1961 Beatles, and let set B represent the members of the 1964 group. We will use the roster method to list the elements of each set. So set A is represented by curly braces with the names of John Lennon, Paul McCartney, George Harrison, Stuart Sutcliffe, and Pete Best, curly braces. Set B, the Fab Four, is John Lennon, Paul McCartney, George Harrison, and Ringo Starr. So as you can see, these two sets are not the same. So part A here is I'd like you to imagine that all members listed above in each of these sets are still alive, and we're going to plan a reunion. Now notice I have union underlined. So this is a little mnemonic device. It's a little way for you to try to remember what the union of two sets would be. So if you can remember this example or the idea of a reunion, it might help you. So list the members who come to the reunion and label this set C. So who would come to the reunion? Well, if the Beatle was in the band in 1961 or in the band in 1964, they would come. If they were in the band in 1961, like Stuart Sutcliffe, but not in 1964, they would still come. So it would be the individual Beatles from both of these bands that would come. That would be the union. So you would list each of those members here. You'd start with the curly braces. I'm now going to be a little more efficient and list each individual Beatle by their initials. So there'd be John Lennon, Paul McCartney, George Harrison, Stuart Sutcliffe, Pete Best, and Ringo Starr. So that represents each individual Beatle that either played in the 1961 Beatles band or the 1964 Beatles band. And they would be the ones that would come to the quote unquote reunion. So technically the set of reunion members above represents the union of sets A and B. And it's denoted with this symbol here, this U type symbol. Notice it doesn't have a stem on it like the U, the capital U we write in the alphabet. But this says A, the set A union with the set B. And sometimes we read it as set A or set B, because either of these Beatles here that we've listed in the union is a member of one or of these sets, one or the other. Some of them are members of both, but we're looking at the Beatles that would sort of be, if we put those two sets together. And notice we don't list a Beatle more than once. They can't show up at the reunion more than once. You know, there's no clones. All right, so based on the reunion, explain in your own words how you would form the union of two sets. So this is for you to write out whatever would help you remember this. And you could use this specific example with the Beatles and the reunion, but write it in your own words, and then that will make more sense for you. So I'm not going to fill this in. Okay, now we're going to look at another idea. We're going to let set D represent the set made up of members common to both bands. So this would be like an overlap. What members of the Beatles appeared in both 1961 and 1964? They're common to both. Well, if we go up and look at the sets A and B, and we use some visual here with the highlight effect, say, for example, of the names that you see in both. So I see John Lennon in both sets. I see Paul McCartney in both sets. They're common to both bands. George Harrison is common to both bands, and that's it. Those are the only three Beatles that are common to both bands. That's the intersection of those two sets. So it's John Lennon, Paul McCartney, and George Harrison. So set D represents the intersection of sets A and B, and it's denoted by this upside down U. Some people read that as set A and set B. So what Beatles are in the 1961 band and in the 1964 band? Again, write in your own words the best you can to represent for yourself what you think the union of two sets would be. Excuse me, the intersection. Okay, so now let's look at intersection and unions with sets of numbers versus the idea of people. So the first set we're looking at here is in interval notation, and we want to graph this interval on a real number line. So let's just recall a little bit about interval notation. So we're working on a real number line, and we're dealing with all the numbers between 1 and 4, and we're not including 4. So here, endpoints not included in the set because the parenthesis tells us they're not included. So again, some of you may represent it this way with the open circle. That might be what you're used to. But with our particular book and our author uses exactly the same notation, the parenthesis at 1, the parenthesis at 4 to not include those endpoints, and then you shade in between, all numbers in between 1 and 4. Okay. Now directly below that, I'm going to graph the interval 2, 8. And this time I notice a difference. I see that we have these brackets here, which means we're going to include the number 2 and the number 8. So 2 would be right around here, and 8 would be out here. And I'm going to include it. So if you were working with probably another version of the real number line, graphing sets on real number line, when you include the endpoints, it's all of the numbers between 2 and 8, including 8. So that's why I have a solid dot to include them. If we look at our interval notation and using our number line, we would say, okay, now at 2, I'm going to put a bracket to say 2 is included, and then out at 8, I'm going to use a bracket. So now I've represented both of those sets of numbers on a real number line, and now I'm being asked to find the intersection of these two sets. And remember, the intersection would be the numbers that these two sets have in common. So as if you just basically put one under graph under the other, you could start at 2, and the first set includes the number 2, and the second set includes the number 2. And then if you think about these arrows going between these two number lines, they would include all the numbers up to 4, but not including 4, because 4 is not in the first set. So you would have a parenthesis at 4. And then the first set doesn't have any numbers greater than 4, so even though the second set does, they're not included in the intersection. So this is how you would represent the intersection of those two sets using interval notation. And as I mentioned, you'll be using interval notation quite a bit in your homework in my math lab. Okay, absolute value definition, part 3, and this comes up early in your book. And I think many of you would be able to tell me what the absolute value of a number is. And many of you know that the absolute value is always representing a positive number. The absolute value of any number, the answer to an absolute value, is the number that has no relationship to the fact of whether it's to the left or to the right of 0. It's what's the distance from 0. The conceptual idea here is the distance from 0. So -2 would be 2 units from 0. +2 would be 2 units from 0. So the answer, the absolute value of -2, the absolute value of +2 is 2. Okay, so let's take a look at this definition. Notice the definition of the absolute value is done using 2 pieces. It says the absolute value of some number x is the same as x if x is a non-negative number. In other words, any number greater than or equal to 0. So if a number goes into the absolute value symbols greater than or equal to 0, it comes out looking exactly the same. That's represented over here on the graph by this line right here that goes from 0 and this continues out. So whatever you are when you go in to the absolute value, if you're a non-negative number, you come out at exactly the same height as you go in. Okay, so absolute value of 4 is 4. Now, some students look at this next part, the absolute value of x equals, and if you read this as -x, you're setting yourself up for like a misconception. That dash, when it's in front of numbers, reads negative. But when it's in front of a variable, it's better to say opposite of x. So notice, what types of x are we dealing with now? We're dealing with all of the x's that are less than 0. That's all of our negative numbers. So if I put a negative number into my absolute value, it comes out looking like its opposite. It comes out as +4. If I put -4 in, it comes out being +4. That's the opposite of -4. 4 is the opposite of -4. Okay, so we're not saying here that the absolute value is a negative number. We're just saying if we happen to take a number that exists on the number line less than 0 and we take its absolute value, we don't pay attention to the fact that it's negative. We just want to know what's the distance it lies to the left of 0. And the distance is represented by a positive number, and it's the opposite of that number, because the opposite of a negative number is positive. So I hope this visual here, along with the algebraic statement, helps you. As you can see, this graph, every single y value on this graph is above the x-axis. They're all positive, and that's what you know as your idea of absolute value. All right, so I think that answers A. So now we're going to play a little game called Sometimes, Always, or Never. And please answer whether the following statements are always true, sometimes true, or never true. If your answer is sometimes or never true, either change the statement so that it's always true or show a counterexample. And a counterexample just shows why it's not true. So this says the opposite of the absolute value of x is negative. The opposite of the absolute value of x is negative. Well, some people approach this by saying, well, since I know the absolute value of x is always a positive number, and that's where you go wrong. That's where you're forgetting one number. Okay, so most students think of this as the absolute value of x is always a positive, and the opposite of that is always negative. We'll always make it negative. This is always true. And you know what? If it wasn't for one number, you'd be absolutely correct. That one number is 0. The absolute value of 0 is 0. The opposite of 0 is 0. And 0 is neither negative or positive. So this is sometimes true. So this is an example of a counterexample right here. This shows why this statement is only sometimes true. You could have also changed the statement to say that the opposite of the absolute value of x is sometimes negative, if you wanted. That would be a way to change the actual sentence itself. All right, now let's take a look at the next one. The absolute value of the opposite of x is negative. Well, it doesn't matter what I do to x inside these absolute values, and it doesn't matter whether x is positive or negative inside these absolute values. What I do know is when it comes out of these absolute values, I'm looking at the idea of distance, and that is never negative. So that's never true. Right, the next equation is interesting. It looks at subtraction of two numbers. And it says that regardless of the order that I subtract two numbers, whether I say A take away B or B take away A, if I look at the absolute value of those numbers, they're equal. And when you subtract two numbers, you get a result, the difference of those numbers. If you reverse the order, you get the opposite number. So when you write A minus B, it doesn't equal B minus A. They are opposites of each other. So you could say this, they're opposites. The subtraction of A minus B is the opposite of B minus A. But since these are opposites, their absolute values will be equal. So this is always true. Now the next one I've put in here because we're going to deal with this in a little bit. This says that the positive square root, that symbol asks for the positive square root. And x squared has two square roots. It has a positive square root and a negative square root. But when you ask for this square root, you're asking for the positive square root. If you wanted the negative square root of x squared, you would do what you always do. You'd put a dash in front of it. Okay? So since this is asking for the positive square root of x squared, if you put x in between these absolute value symbols, you're ensuring that your answers on both sides of these equations would be positive. So this is always true.